Today, we are going to explain the transformed area method and find the stresses at various locations of a doubly reinforced beam. So let's draw the beam. The beam is doubly reinforced top and bottom. There are four number 9 at the bottom, four number 9 bars at the bottom, four number 9 bars at the bottom, and two number 9 bars on the top, two number 9 bars at the top. The beam is assumed cracked, and since the beam is cracked, so the neutral axis should be somewhere around the top of the beam. So let's say this is the location of the neutral axis, which is at a distance of y from the compression fiber. And our goal is to find what is the stress at the steel, which is right around here at the center of the steel, and that distance is given by these numbers: 2.5 inch to the compression reinforcement. This is 15 inch from the compression to the tension reinforcement, and this is 2.5 inch again. The entire beam height is 20 inch. Okay. The beam width B is 14 inch, and our D is going to be 15 plus 2.5 is 17.5 inch. Okay, so as we know that in the transformed area method, the reinforcement in the compression side is assumed to, due to creep in concrete, assumed to have double as time goes by. The compression will double as time goes by. So first of all, these are the given values. N equals 10, the modular ratio, which is where N is ES, modulus of elasticity of steel over modulus of elasticity of concrete. And the moment given M is 118 feet. Okay. So first of all, we have to locate the neutral axis. Locate the neutral axis. Okay. So to do so, we just assume that the neutral axis is at a distance y from the compression fiber. So that will give us that from the neutral axis, if I draw a red line on along the neutral axis, from the neutral axis, the area moment about the neutral axis in the compression side must be equal to the area moment on the tension side. On the tension side, we do not include the concrete because it is in tension and it does not contribute to the strength. On the compression side, we include the strength of concrete in calculations. So let's take area moment. It's going to be 14 times y times y over 2. That's just for the concrete. Plus, we have the reinforcement, which is to number 9 is 2 inches square, AS prime. AS prime is 2 inches square, 2 inches square, and AS is for number 9, which is 4 inches square. So when this reinforcement is taken out, the thing works like this, that if we transform this area and this area comes out, and we fill this in, and this is going to be, this total area is going to be 2n minus 1 times AS prime. Okay, so that is the thing, and now that area will be 2 times 10 minus 1 times AS prime is the compression area, which is 2. And the moment arm will be y minus 2.5. That is the compression area moment, and that must be equal to, let's box it out so that doesn't interfere with our calculation. That must be equal to n times AS, which is 10 times AS is 4 times 15 plus 2.5 is 17.5 minus y. So if we solve this, we get y equals 6.45 inch. That means the location of the neutral axis is 6.45 inch from the compression fiber. Next thing we want to determine is the cracked moment of inertia, since the beam is cracked. Cracked moment of inertia is going to be I correct. It's going to be BH cube over 4, 3, 14, 6.45 cube over 3. That's for the top part. And then plus the compression area will be 2 times 10 minus 1, 2n minus 1 AS prime. So times 2 times 6.45 minus 2.5 is squared. So 6.45 minus 2.5 squared. Plus, for the tension reinforcement, we have 10 times 4 n times AS times 17.5, 17.5 minus 6.45 squared. This is moment of inertia, so should be squared, AD squared. And the result is 6729 inch power 4. 6729 inch power 4. Okay, so now we want to find what are the bending stresses. And to calculate the bending stresses, what do? You know that the bending stresses F or sigma is M Y over I cracked. Since the beam is cracked, so we will use the crack moment of inertia. So bending stress on the concrete is on compression fiber is my over m is 118. This is in cubic feet. So multiply by 12,000 to make it pound and inch. And y is the distance from the neutral axis to the point of the compression fiber. So let's say this is FC right here, which is 6.45 inch. And I crack moment of inertia is 6, 7 to 9. So the stress in the concrete is 1357 psi. And bending stress on steel. So bending stress, uh, this is stress. Bending stress on steel is, it is going to be n times, because the bending stress in steel will be right here, and that will be n times the stress in concrete. So n times m and y, I cracking. So n is 10 and m is 118 times 12,000 to make it pound inch, and the y in this case is 17.5 minus 6.45 and 7 to 9. So that is 23,253 psi. 23,253 psi. So that's the answer. Okay. So let's stop right here, and we stop recording.